So today we are continuing the lectorium on algebraic graph theory in the frame of the Mathematical Center in Akademgorodok. And we are resuming the mini course devoted to the geometrical topics in the theory of self-similar fractals. And the third lecture is in this course is titled The General Position Theorem and Some Long-Awaited Counterexamples. And I'm glad to introduce the lecturer of this course and of this particular lecture, Professor Andrei Tetenov from Sobolev Institute of Mathematics and Novosibirsk State University. Please, you're welcome.
Hello, everybody. So today I will discuss some very interesting counterexamples in the history of fractal geometry. And the main tool for obtaining this counterexample is so-called general position theorems. So consider a system of contracting similarities on Rn. A compact non-empty set K is called the attractor of this system if K is the union of its images under this contraction similarity. So we call the subset self-similar with respect to the system S. If the system S, if there is a such open set O that for each I, Si of O lies in O and the images of O lie inside O, and images of O do not intersect for distinct Ij, then we say that the system satisfies the open set condition. This condition is the main condition for the absence of essential overlap of the pieces of the copies of the attractor. But the problem was that to check the open set condition, the checking of open set condition is not an easy job, because sometimes the attractors may be quite complicated. The simplest case is if the copies of the attractor are disjoint. For example, let us look at the picture. Do you see the picture? Yes. For example, if you have a self-similar set whose copies do not intersect each other and they are compact, therefore we can consider such an open set that its images will not intersect each other. So if the copies absolutely do not intersect, then it's easy to find such an open set. Oh, sorry, I didn't show you the picture, I see. Oh, now the picture is here. Do you see? Hello?
Yes, yes.
Yes, is it okay?
Yeah.
So now let us proceed further. Let us proceed further. So it was unclear how the open set condition relates to the actual sides of the overlap. So even in 1992, in their work as self-similar set 7, Christoph Band and Siegfried Graf wrote, "We were not able to prove the open set condition for all self-similar set for which the pieces intersect in a single point. So single intersection property did not, it was not possible to prove the open set condition in the case of single intersection property. So there were many attempts to prove this, that single intersection property implies open set condition. So Christoph Bandt and Rauch Wei showed quite later, maybe in 2009 or later, that, let me check the date, in 2007, in 2007. Okay. So they proved that finite overlap implies open set condition for connected self-similar sets in the plane. So there are two questions that naturally arise in this case. First one, does single intersection property imply open set condition in disconnected case? And second is, does single intersection property imply open set condition for connected self-similar sets, but not in plane, but in R3? So these questions were opened for many years. Our solution of this problem took some time. So the problem of violating open set condition for one point intersecting self-similar sets in R3, and for connected ones, this solution was found in 2015. I knew about this problem in 2009, so it took about 5 years to find the solution. And second question, that open set condition is not fulfilled even the attractor is disconnected, and it happens in the real line. This problem was solved by me and Kirill Kamoludinov in 2019, but it was published in Nonlinearity in 2020. So the first solution was the following. There is such system of contracting similarities which does not satisfy open set condition, which satisfied single intersection property, and whose attractor is a Jordan arc in R3. And the other theorem is the following. There is a system of contracting similarities on a real line whose attractor is totally disconnected, yes, and contains the points 0 and 1, which does not satisfy open set condition. The only intersection of copies, there are two copies, Ki and Kj, for which the intersection is non-empty, and it is a single point, which is Si of 0 and Sj of 1. And third, the Hausdorff dimension of this set is equal to the similarity dimension of the system, but the measure, since the open set condition is violated, the measure should be zero, because positiveness of the measure implies open set condition. So the main problem which we met solving this problem was to understand what happened if we take a self-similar set and begin to move its copies. But if we move the copies of a self-similar sets, then the smaller copies move with respect to each other, and at these moments and change happens on all the scales. Of course, there are standard intersection theorem. I will comment on this on a picture. Suppose we have two sets in Rn, for example. For example, if we have two planes or hyperplanes, and we are in Rn, and this dimension is M1, and the dimension of the second set is M2, then the dimension of the intersection will be how much? M1 plus M2 minus N. This is well known. This is well known. And if we begin to move this set, and this, in almost all cases, this dimension will be the same. But of course, there are degenerate cases. If we take, for example, two lines in the plane, then if they don't intersect in one point, then they coincide or don't intersect at all. Therefore, the same situation holds for all kinds of dimensions. And this was written in Falconer's book, that if E and F are Borel subsets of Rn, then for almost all translations of the set F with respect to E, the dimension of the intersection will be less or equal than maximum of dimension E multiplied F minus N for almost all X in Rn, with the only exception when E and F coincide. And there is a corollary. If E and F are Borel subset of Rn, and G is a group of motions, yes, it's translations or congruencies or even similarities, then for almost all elements of this group, the dimension of the intersection will be less or equal to dimension of the product of E and F minus dimension of the whole space. But what is the problem with this situation? The problem is the following. We have rigid motions of F, or at least the similarities of F. And other transformations of F are not allowed. And what happens if we have a self-similar set? If we have a self-similar set, the following thing happens. For example, consider the way how we transform a line, for example, to a Poncke curve. Yes. Because we can take this 2 point and change this angle, yes? But if we change this angle here, then we also change the angles at any of the smaller triangles. So the whole picture will move at all scales. And what can we say? For example, if we take some line and consider the intersection with this line, then it's impossible to catch all the changes. What to do? What to do if we have two self-similar sets? For example, in the space, and begin to move them. But they don't move rigidly, but they change at every smallest piece of this set, and both sets will be changing. How can we make any decision? Is it possible to avoid the intersection of these sets by very small deformations of these sets? So the main tool for studying of the deformations of self-similar sets, sorry, I don't understand what happens. Yes, is the general position theory. So there will be such formulation. Suppose we have some set of parameters Bn, and A will be some basic self-similar set. And for each x from the set of parameters, we have some continuous map, phi and psi, which send A to Rn continuously with respect to these parameters. So you see, we have a family of, for example, homeomorphic embeddings of the same, so or the same or of different self-similar set to Rn. So nothing is said about these maps, phi and psi. But we need to establish some order in these maps. And first will be that these maps are alpha Hölder with respect to t. It's a natural restriction, yes? For example, if you have a map which sends the interval to some variation of Poncke curve, then it's Hölder. The degree of this Helder map will be logarithm of 2 with respect to 3. It's the number which is inverse to the dimension, 1 divided by dimension. So they are alpha Helder with respect to t. And second, we need very important condition for any two parameters. Oh, sorry. Yes. For any two elements of the set A, the function f of x ts, this is a distance between the image of the point T and image of the point S in different copies of the set A. This distance is by Lipschitz with respect to x. So if we move x slightly, then this difference also changes proportionally with this movement. And this is enough. It implies that Hausdorff dimension of those set x for which phi of xa and psi of xa have non-empty intersection does not exceed 2 dimensions of A divided by alpha. Now, this theorem is very easy to prove. So the proof of this theorem is quite elementary. So the condition of the theorem was that these maps are alpha Helder with respect to t. So since these maps are alpha Helder with respect to t, then their difference f of x is t. You see this difference? Yes? Do you see? Right?
Yes.
So it's phi of xt minus psi of xs. X is a parameter. So we have some parameter and we have different points of the images of A. And we change the parameter. Oh no, we change the parameter x, and this difference changes accordingly. So since f of x st is by Lipschitz with respect to x, then if f of x st is equal to f of x2 st, then x1 is equal to x2. Right? If the difference of these two because any change of x leads to some change of f of xt. So there is only one x for which this value is the same. So then, therefore, the equation of x st equals 0 specifies an implicit function g of st defined on some closed subset in A multiplied by A. Let us look at the picture. So we have a set A, yes? And this set A is mapped to phi of xa this way, and by the map psi of xa, some other way. Yes. And we took 2 points, one point on f of xy corresponding to some s, and a point on psi of xa corresponding to the some point t. And now we change the parameter x. And if we change a parameter x by some delta, then this difference cannot remain the same, therefore it changes, right? Changes. And for example, if we have for some parameter phi of xa and pi of xa and psi of xa intersected at the image of the point S and the image of the point T, then after changing this parameter x, this intersection point disappears and becomes some other point. But for each pair of parameters of ST, there is only possible point of intersection according to this condition. So therefore, for each S and T, there is unique point X for which f of x xt is 0, for which these two curves, psi of xa and phi of xa, intersect in some point. Now consider 2 points, g of s1 t1 and g of s2 t2. Yes. So this is a point corresponding to intersection by parameter s1 and t1, and this is a point corresponding to intersection of all of the parameters s2 and t2. Then f of x s1 t1, f of x2 s1 t1 will be greater or equal. You see, f of x1 s1 t1 is 0. F of x2 s2 t2 is 0. So f of x1 x2 s1 t1 is f of x1 x2 s1 t1 minus f of x1 s1 t1. Therefore, it's greater than x1 minus x2 divided by the Lipschitz parameter. At the same time, the f is alpha Helder with respect to s and t. Therefore, f of x to s1 t1 will be less than m multiplied by the norm s1 minus s2 and t1 minus 2 to the power of alpha. Therefore, x1 minus x2 will be less than lm multiplied by this to the power of alpha, right? And what does it mean? That g of st is alpha Helder on the set P. The set P is the set of those points for which this intersection is non-empty. Yes. Then the dimension of the image of P will be less than 2 dimensions of A, because P is a subset of A. Yes, P is a subset of A multiplied by A. Therefore, the dimension of P is less or equal than dimension of A multiplied by 2. And since this map is alpha Helder, then we divide this thing by alpha. And if this dimension is less than dimension of the set in which we are, if it is less than dimension of the set of parameters, yes, Bn, then for almost all points in the Bn, the images phi of xt and psi of xt would not intersect. So this allowed us to find a totally disconnected set on the real line for which satisfies one point intersection property, and at the same time it doesn't satisfy open set condition and weak separation property too. So what we do? First, we take some PQR less than 1 divided by 36. So we see there are 6 pieces, yes? And also there are 4 gaps. For that reason, we take PQR less than 136 and put H and A equal to 8/15 and 3/15. And we get the system of similarities. First is Px, second is Rx, and this is a contraction to 1. Six. The second is Rx and minus Rx for this one. And these are 2 maps which go in opposite order. Therefore, in this copy, we have images of this endpoint, yes, which are in the beginning, and in this copy, we have images of this point, which is near ones. But suppose Px, P and R, if we change P and R such way that the ratio of their logarithms doesn't belong to Q, then by Kronecker theorem, we'll have the images of the point of all points will form a sequences in which the members of these sequences approach each other as close as possible with respect to the distance, to the point 1. So if Px and Rx are P and R are not logarithmically incommensurable, yes, in this case, weak separation property is violated because there will be, how to say, well, I will write this relation on the paper. One second. Sorry, I lost my. So we have S3 multiplied by S1 to the power of m. This will give us the sequence of copies approaching this point here, yes. And when we take the other piece, the other copy, the arrow shows to the right side, then there will be the copies of type S4, S6 to the power of n. Yes. And in any case, S3, S1 to the power of m minus 1 multiplied by S4, S6 to the power of n. Such compositions, there is a sequence mk, nk, such that these compositions will tend to identity. And this means the violation of weak separation property. So the weak separation property is violated, but what happens with the copies? Since these sets approach each other as close as possible, we need to avoid the intersection of these sets everywhere apart from this point, apart from their common endpoint and the point with the coordinate h. You see. So we do the following thing. We take Mn, P and R. So we have the sets with parameter P, Q, and R, right? Right? So there are three parameters. P, this is here. Q, this is there. And R is at the other points. So we have the set K, P, Q, R. And for this set, depending on these three parameters, we consider the pairwise intersections of S3, S1, 1 to the power of m, Si of K, and S4, S6 to the power of n of Sj of K. This set are placed somewhere. They do not approach this. They may come close to the point H, but they never contain the point H. Yes, they have some distance from H. And we need to find such parameters P, Q, and R for which all these intersections are empty. So let delta of Mn of PR be the set of all Q for which this intersection is non-empty. using for each P and Q and each M and N, we show that the set delta Mn of PR is the set of all parameters Q for which this intersection is non-empty. It has dimension 2 logarithm of 6 divided by logarithm of R. Since 6 is more than 1 and R is less than 1, so we write the minus. And this number is always smaller than 1, and it is separated from 1. Therefore, we obtain the result that taking the union of all these sets delta Mn of PR, we also get the set whose measure is 0 on the unit interval. Therefore, for almost all values of Q, because PR is fixed, for almost all values of Q, the intersection is 1 point. And this proves our first theorem. Now let us proceed to the second one. How to build a self-similar curve in R3 for which its pieces would approach each other as close as possible, but without any intersection of these pieces. So we built such a zipper. So we take some angle beta 0. Yes. Take some angle beta 0 and build a broken line or polygonal line in the plane such that this copy and this copy are just on this beta 0 line. Then if we apply these mappings, which are shown here, then we'll have the image of this curve in this place and in this place. And these two copies will approach each other. But here we have the contraction ratios. One contraction ratio is here, and the other contraction ratio is here. And we not have the contraction ratios only, but we also have rotation angles. So we are in R3, therefore, these two maps are not only contraction, but also the rotations in the axis X, in the X-axis. Yes. We choose such contraction and rotation that they possess the following property. So now this is a picture of the attractor, of some approximation of the attractor. Do you see? Yes. So we have this copy is here, yes, and its first slope is here. And this copy is here and its second slope is here, right? So here we go in this direction and there we go in that direction. So these two pieces approach each other. But we need that they approach each other, but do not intersect. And therefore, we also use the same general position theorem. And initially, this general position theorem appeared just for this example in 2015. Yes. So the problem is to choose the contraction ratios R for this copy and R large for this copy. And also rotation angle alpha for this copy and beta for this copy. So these copies will be rotated by the angle n alpha here and angle m beta here, yes? And contracted by the ratio r to the power of n, r small, and r large to the power of n. There is a very interesting consequence or corollary of Kronecker theorem. Consider the multiplicative group in C generated by two complex numbers, r multiplied by e to the power I of I alpha and eta is r large multiplied by e to the power of I beta. What is wonderful that for Lebesgue almost all psi and eta, this group G satisfies wonderful property. For any initial Z1 and Z2, there is a such sequence NK-MK that this limits is 1, and this limit is this one. What does it mean? I will explain. I will explain it on a picture. So here we have a complex plane and we have a point 0. Yes. And we take two complex numbers, psi and eta. And if we begin to multiply these numbers, we'll get a sequence. So the sequence will be placed on some logarithmic spiral for each number, yes? And these logarithmic spirals have different slopes, so these spirals will intersect each other infinite number of times. But what is most striking, that for each ray passing from 0, there will be a sequence of pairs of points, eta to the power of nk and psi to the power of mk, that these pairs approach each other and also approach this ray. And these two numbers are just the ones we need for building the example, which I supposed. Yes. So when we have such a group, then we apply. We have some additional parameters for this zipper, and the parameters are the following. So we fix these contraction ratios, this and this, but we can slightly change this angle, the angle between these two rays. We can slightly change the rotation angle when we send the this cone to this one. Yes. So we have all kinds of rotation angles from 0 to 2 pi. And we can slightly change this rotation angle. And finally, we can slightly change this length. So these are three parameters which do not correlate anyhow with psi and eta, which are fixed here. So psi and eta give us the result that in this sequence of these copies, there will be such nk and mk that these copies will approach each other as close as possible. And these three parameters are in this form, are parameters which run through some three-dimensional ball. And for these three parameters, we checked the conditions of this theorem. Yes. So in that case, T and S will be points from unit interval, which give us the structural parameterization of the zipper, and X is the triple of parameters of which change the position of this copy. And we prove that this function is bi-Lipschitz with respect to the X. And alpha Helderness is provided by the condition that the similarity dimension of this curve is almost the same. Therefore, we have that dimension of the set of parameters divided by the set of, well, A here is the unit interval, yes, and alpha is Helder coefficient. Therefore, if alpha is less than, so the A has dimension 1, alpha is less than 1 divided by 3 divided by 2, then we have that this dimension will be smaller than 3, and it means that for almost all the values of these parameters, these two pieces would not intersect each other, and therefore this curve satisfies one-point intersection property, and at the same time the weak separation property and open set condition will be violated. So I think that is enough for today. Do you have any questions?
But in the previous slides, there was a P, which is a subset of A cross A.
Oh, please repeat your questions. I didn't hear it well.
I'm asking, there was one set P, which is a subset of A cross A.
Oh, P is some subset of A cross A, but its dimension is less than dimension of A cross A. But A is unit interval in our case, yes? So the dimension of A cross A is 2. So dimension of P is less than 2. Sorry, P. Let me look at this formulation. So 1 second. Yes. So A cross A. A is, in our case, we have unit interval, right? Bn is a 3-dimensional ball. Yes. And so we have 2 divided by alpha. And alpha is 1 divided by the dimension of this curve. So dimension of this curve can be computed using this just as a similarity dimension, right? If we make this angles sufficiently small, then we can make this similarity dimension as close to 1 as possible. But in any case, it will be less than 3 divided by 2. So it's the problem of choosing the angle and choosing the diameters of these copies. But essentially, it depends on beta 0, on the angle beta 0.
How is that phi function and psi function chosen? It is an arbitrary choice?
No. These phi psi, what? So you see here, there are 2 copies intersecting, approaching each other at this point, you see? So at this point, here we have the image of this copy, right?
Yes.
And there we have images of that copy. So this map, the map which sends, if you take unit interval, then send it to this copy, and then send here, it will be phi.
Okay.
And if you take the unit interval, send into this copy, and then send to that one, we have psi.
Okay.
So phi and psi are, and the set of parameters is defined by the position of this point in some neighborhood of this point, and the rotation angle.
Okay.
Additional rotation angle. It's 3-dimensional set of parameters, and we find that the subset of the set of parameters have dimension less than 3. Therefore, for almost all values of these parameters, we have empty intersection.
Okay.
Of these pieces, of these ones. So really, it was very... so the computation of all these small values and all this is a headache, but the idea is very simple.
Well, any other questions, comments? So if this is not the case, then let us thank the speaker. Thank you for the nice exposition of the general position theorem and the examples, which are really smart. Thank you.
Thank you very much. Maybe sometimes later I will give a more detailed exposition of this question. I hope. So thank you for your patience, and I think we will develop this topic to a much more large extent. So bye. Let us finish our talk.